This is the Pfund series for the hydrogen atom, and it reads, in the line spectrum of atomic hydrogen there is also a group of lines known as the Pfund series. These lines are produced when electrons excited to high energy levels make transitions to the n equal 5 level. Determine the longest wavelength and the shortest wavelength in the series. Identify the region of the electromagnetic spectrum into which these lines are found. So the equation to write down would be 1 over lambda equals the Rydberg constant times 1 over the final NF squared minus 1 over the initial N, and then we're supposed to come up with two results. Oh, I'm going to write that differently. Hold on. And maybe I like blue better. We're supposed to come up with lambda for the shortest, the shortest wavelength and the longest wavelength for the series. Both of them would be in nanometers, should be in nanometers. The Rydberg constant is given as 1.097 times 10 to the 7 meters per meter. And then if we want to have those results in nanometers, shift the decimal point 9 times from meters to nanometers. It's 9 times. So by shifting in the decimal point 9 times, instead of 10 to the 7th, we're going to write 10 to the negative 2 because the exponents subtract. So negative 2 here. Of course we could all, and then I put a per nanometer here. Of course I could also write 0.01097, and then the NF is going to be 5 because that's the level for the Pfund series, and then the longest wavelength that we're going to get is for the very next level, for 6, and then the shortest wavelength we're going to get is when this fraction here gets very, very small, because then we have the largest possible number in here and therefore the smallest possible lambda, and that would be if we typed in infinity, which we really can't, but what we could do is we could either choose a very large one or we could simply subtract 0 here by making this very large. I'm going to show that on the graphing calculator. So I'm going to type in 0.01097 times parentheses 1 over 5 squared minus 1 over 6 squared. Enter, invert to get lambda, and so that's 7,458 nanometers, and then I'm going to do it for a very large number here, let's say 9,999, and then again invert the answer. Oops, what did I get there? Oh, right there. Invert the answer, and that would be 2,279 nanometers respectively. A moment ago I said, well, we could also subtract here 0. We could subtract 0 here. Invert, and that's the same answer, because by dividing both a very large number here, this one is going to be in close approximation to 0 anyway, and that's why either way we do it here, we come up with the same result. Okay, on PhET, Physics Educational Technology, there was this nice applet here where we have a light here that shines white light or monochromatic light on here. I chose white light here, so you have all kinds of photons going in. You can see red, yellow, orange, these funky things here. These are ultraviolet, and I think some of these are also infrared, I don't know which. And then they hit the electron, and you see that the electron there, it's on an upper orbit, jumps down and emits some light, and again jumped up to a higher orbit as it absorbs one of those photons, and then it may send out an ultraviolet or visible light. Here are these typical Bohr lines, 656 nanometers, 484, I believe it is, 412, and I believe this one is 390, and then some infrared ones. And the Bohr series is when it jumps down to the second level. The Lyman series is when it jumps down to the first level, and then the Paschen, the Brackett, and the Pfund series is when it jumps down to the third, fourth, and fifth level, and that would be in the infrared. This problem is about the Pfund series in the hydrogen atom. Oops, I take that back. In the helium atom. The Bohr model can be applied to singly ionized helium, Z equals 2. Using this model, consider the series of lines that is produced when the electron makes a transition from higher energy levels into the n final equals 4 level. Some of the lines in the series lie in the visible region of the spectrum. What are the values of Ni, that means the initial, and for the energy levels from which the electron makes the transitions corresponding to these lines? The keyword in here is singly ionized helium. So if this is my helium nucleus, 2 protons and 2 neutrons, and I have a couple of electrons floating around here, not floating around but orbiting it, and then I take one of these electrons away. Well, now I have singly ionized helium, and this is the key thing. Singly ionized helium means only one electron is left, and it reduces itself to actually the Bohr model of the hydrogen atom. The Bohr model itself, it's relatively simple, can really only be applied to atoms that only have one electron left. That means hydrogen with its one electron, helium, if you remove one, you're left with one, lithium, remove 2 and you're left with 1, beryllium, remove 3 and you're left with 1, uranium, remove 91 and you're left with 1. And for that, the spectral lines become really simple. By the way, if the second electron was still there on the helium atom, this wouldn't be the simplified Bohr model, but we would have to contend with positive charge here, negative here, 3 Coulomb interactions between these particles, and it would make the equations really, really tough, even if it's just 3 particles. At 2 particles, it's really easy. Okay, I'm going to actually start out, before I go to the actual problem, I'm going to start out with looking at the Bohr model of the hydrogen atom, and then I'll return here to the helium. So here we have the electron jumping down from a higher energy state to a lower one, and in the process it emits a photon. And if this is hydrogen, then it emits that photon at a certain frequency that is given by the Bohr series for the visible light, where it jumps back to the second energy level. Notice that this is a second orbit, so the electron would actually have to jump down from the third or fourth or fifth or sixth orbit here. And if it jumps down to the first one, then that would be the Lyman series, which is in the ultraviolet, where it jumps down to the first level, and then the Paschen series, it jumps down to the third level, and then actually the Pfund series would be for the hydrogen atom, that is, it would jump down to the fourth level, and that would be in the infrared as well. On hyperphysics, and by the way, these images here are from our book. on hyperphysics. Here we go. So it would jump down to the first level for the, let's see, was it the Lyman series? Yep, Lyman series, and then second level down to the Balmer series, and then here to the third level from a higher level would be the Paschen, and to the fourth would be the Pfund series. And these are named after people who discovered those. Let me see if here, oh, okay, here are the Balmer lines, and as you can see, jumping down to the second level. So these series are named for various physicists who discovered these particular series, and the calculation, even though to the uninitiated this might look hard here, 1 over n squared minus 1 over n squared to calculate that, but to somebody who is in physics it hardly gets any easier to calculate. Here would be the visible spectrum of the hydrogen, and I took, and you notice red, turquoise, and purple or blue, and I took photos of spectra quite a while ago, probably 15 years ago by now. And here we can see the hydrogen spectrum, the red line, the turquoise, the first purple, and the second purple, which to the human eye is so close to in the ultraviolet that we don't perceive it. We only see 3, but the camera was able to pick up all 4 of them. Spectra such as these here, this is actually from a lab that I have for my astronomy students, and I believe I put them in reverse order, like this last one here would be argon, and then CO2, helium, hydrogen, and so on. This one here is helium with 2 electrons. Now, these kinds of spectra are being used for example for identifying stars and seeing what kind of elements they have in their atmosphere, respectively, how strong those lines are, and that gives us a lot of information about stars. By the way, the helium that you see here, again, this is the helium with its normal 2 electrons, but the spectrum for the helium with just 1 electron looks different. And I'm going to look at this one here. This here is a stellar classification with the hottest stars having a temperature of about 30,000 kelvins. That's a surface temperature. Only the core is a whole lot hotter. That's approximately 50 to 60,000 Fahrenheit on the surface. And notice here it says lines of ionized helium and weak hydrogen lines. And this classification of O here, it goes O, B, A, F, G, K, M. So the hottest ones are O here. Notice it says hydrogen here, and it turns out that these, where it says ionized helium, weak hydrogen lines, where that single ionized helium here has the same spectral lines as the normal hydrogen. That means that the Pfund series in the ionized helium, which is in the visible part of the spectrum, are actually virtually the same lines as the Balmer series for the hydrogen, and I'll show that in a little while on how that comes about. And here just a comment on that, where it says that Pickering, as he observed a hot star in 1896, mistaked these ionized helium lines for a form of hydrogen because they were so close to those here. And notice these colored numbers here. This is a different unit. It's not nanometers, it's angstroms, but we can read this here as 454 nanometers, 485 nanometers, 541 nanometers, 656 nanometers. And if you look at these numbers here, the 656, the 485, and there's actually the 412 here. It's kind of missing there. That actually is these are actually these two green ones here overlap totally with the Balmer lines for the hydrogen. Okay. I'm still not ready to do the actual problem, but I want to pull up this one here from PhET, Physics Educational Technology. Again, it's quantum physics, and I looked up the hydrogen atom, and here's an experiment where the question mark simply stands for, well, there's a hydrogen atom there, but we don't know how it looks like. So turn on all the white light here, by the way, when I do monochromatic here, this here would be ultraviolet, these here would be violet, blue light, turquoise, green, yellow, red light, and it's kind of like pretty how they made this particular one. And then when I turn to white, well, you get all of them. And notice that in this experiment, once in a while, one is being sent out. You just saw it going to the right. So it hits something in there, which presumably is the electron, kicks it up to a higher level by absorbing that energy, and then as it jumps down, it's sending off. There you saw a couple of red ones going on, and there was an ultraviolet going out here. So it's sending out these photons. Okay, here's the different models of the hydrogen atom in series from classical physics to quantum physics. So if the hydrogen atom was a billiard ball, then this is how it would look like. Well, we're not observing that. Remember, this is the actual experiment, and our model has to fit the experiment, and you don't see these going all over the place, so it can't be the billiard model. Here's the plum pudding model, and actually when you look at it, there was one going out this way a moment ago. Let's see, to the down, upper right, upper left, upper right, and these are all ultraviolet that's being sent out, down, and so on. I notice this is really kind of confusing as you look at this one here. I just try to pay attention, or I just focus on the middle of the screen, and on the corner of my eye I'm able to see where the photon is going that is being sent out. So plum bottom model actually isn't too bad here. It kind of models the experiment, but of course plum bottom model doesn't work for Rutherford scattering, and I don't know why they put this one in here. Classical solar system atomic model, and that makes kaboom. Okay, the Bohr model, again, this is all kinds of white lights, so all kinds of photons are being sent out, and again I'm focusing on just the nucleus. So out of the corner of my eye I can see what's happening. So lower left, and the electron being kicked down there, you can see it down, and then being sent out ultraviolet radiation, and that describes it pretty good. That's what we saw earlier. When I go to a de Broglie model here with the de Broglie wavelengths, vibrations inside each orbit, then that pretty much looks the same as well, also fulfilling the experiment. And to the upper left, and where'd it go? Upper left again. Some of them I missed. Maybe you see them down, and so on. Okay, so this is what's happening. You send particles in, they collide with I'm sorry, this is photons. You send photons in, they collide with the electron, are being absorbed. The electron jumps to a higher orbit, and as it jumps down consecutively, it cascades down actually, it sends out radiation in any kind of direction, and that is what we see experimentally as well. I wrote down the entire formula for the wavelength. I realized that this is here all the Rydberg constant that's given in the book, but I needed to rewrite the whole thing because I need that z squared here. Notice that for the Balmov series for the hydrogen, of course for hydrogen this is 1 here, 1 squared is 1, and it jumps down to a final state of the second orbit. So this is a 2 right here, 2 squared. And then notice that when you multiply 1 with 1 over 2 squared, you come up with 1/4 as you distribute the z squared. Now for the Pfund series for helium, this one is a 2, which means this is 2 squared, which is 4. And then the final state that the electron is jumping down to is the 4th orbit. So this one is a 4, which is squared. And then we have 2 squared, as we distribute it, 2 squared times 1 over 4 squared, which is also 1/4, and that is why the Pfund series for the single ionized helium resembles, at least in part, the hydrogen, the Bohr series for the hydrogen atom. So we would get the 656 nanometers, and we do get the 485 nanometers. I believe earlier when I looked at this Pickering article, we also saw 365 nanometers. Okay, finally, doing this problem, we're supposed to figure out what are the energy levels from which it has to jump in order to create visible light, and they say that's between 380 nanometers and 750 nanometers. And for the Pfund series, where it does jump down to NF equals 4, of course it has to jump from the initial 5, 6, and so on, 7, 8, 9, 10, and so on, up to infinity, in order to produce that series. But not all of these may be in the visible range. One of them might be too short and one of them might be too long. So we're going to calculate that. I'm going to write down this formula again, 1 lambda, except this time around 1 over lambda. This time around I'm going to write r and then times z squared. Excuse me. Fortunately, I'm always able to turn off the microphone when I need to cough. Okay. And then we're supposed to figure this and I here, the initial state. And I'm going to do kind of like 3 algebra steps. In one, I'm going to move that removed electron somewhere else. So I'm going to solve for Ni, and if you want to look at the algebra yourself, then there are a few steps in between here that you could look at. So I'm going to come up with 1 over NF squared Of course, I would have to remove this to the other side. I have to divide by this here before I do that. So this one here actually says 1 over lambda r times z squared. Then I get this to the other side. Then I invert everything, and then divide by lambda r z squared. And this is basically what I'm going to come up with. 1 over lambda r z squared. And I said a moment ago, because this one is in the denominator but now shows up on the top here, I need to invert it, so I'm going to put a negative there, and then I need to take the square root, so I need to take a negative 1/2 as implicating the square root, and the negative of course means the entire thing would have to be inverted. And then it's just a matter of plugging in numbers. So this one here would be a 4. The lambda here, I would plug in 380 nanometers and 750 nanometers. I'm going to do that in a moment on the calculator. And then the r here, so this one here, 380, respectively 750 nanometers. And the r here, the Rydberg constant, is given in the book. That's one of the constants I don't have memorized. I think it's 1.097 times something, 10 to the negative something, as I'm paging through the book here trying to find, 1.097 times 10 to the 7th meters to the negative 1. So that's given in the book. And then the z here itself is 2 for helium. Okay, and then I'm going to plug things in. So plugging in would be 1 over 4 squared minus 1 over, Here I'm going to put a parentheses. So it's going to be 300, I'm going to start with the 380 nanometers times the Rydberg constant, which is given in per meter. So I have to convert one of them. I'm going to do this one here in nanometers to meters. So 380 10 to the negative 9 times, and the Rydberg constant 1.097 to the 7th, and it's per meter. So the units here actually divide out, which is good. At the end I'm not going to have any units, it's just going to be a number for the orbital, and then times 2 squared. This is for that the helium has 2 protons, and I'm going to close one parenthesis, I'm going to close another parenthesis, and then I'm going to do it to the negative 1/2. Go, and I'm going to come up with 19.88, and I'm going to interpret that result in a moment. But I'm also going to do the 750 here. Oops. 750, and I'm going to come up with 5.58. And what these numbers mean is that if it jumped from the 5th orbital, then the wavelength, respectively, the orbits have to be between 5.58 and 19.88, and that means if it jumped from the 5th orbital, then the wavelength would be longer than 750 and puts us in the infrared. And if it jumped from anything higher than 19.8, such as the 20th orbit, then it would be shorter than the 380 nanometers that's just off the screen here, or there it is, and therefore it would be in the ultraviolet. So the permitted orbits in order to give us visible light would be between the 6th and the 19th orbit, and so quite a few. And we saw it earlier when we looked at the Pickering article that there were a few more in between the ones that would be listed for the hydrogen. So where the hydrogen has only 4 in between, the helium, the ionized helium, has actually, yeah, I guess, what is it, 5 to 19, about 14. Okay, and with that I'm finally done with this problem.